All right, well, we just took a look at our test in here. Students did well, very pleased with how they did. And so hopefully you did well also on your test. We're beginning chapter 9 now, and I love this chapter. For one thing, there are almost no terms to have to know. Very little to memorize. It's great. It's pretty much all math. All right, so we're going to begin a section talking about concurrent forces. Now remember, force is a vector. I think we had the illustration of, was it Kendall on the edge of a cliff? And was it Audrey who came running up behind her and applied a force? And we said if she pushes, if it's a force away from herself, then she's a murderer. But if Audrey pulls toward her with that same amount of force, then she's a good friend who tells Kendall life's not this bad. We can talk this through. Kendall's not actually depressed. Are you depressed, Kendall? Oh, never mind. Wrong person to pick up. Just kidding. Anyway, but force is a vector, meaning magnitude and direction both matter. Concurrent forces then are multiple forces that act at the same time, just as concurrent vectors. Multiple vectors that act at the same time. Concurrent forces would be multiple forces that act at once. And we actually looked at a couple of examples even in the last section as we first looked at this whole x and y component thing. I think there was a problem where we had a guy who was, well actually I think we looked at velocities, didn't we, with that one? But I think we looked at one problem where like multiple people push from different directions. What's the resultant? That's what we're largely going to be doing. Now I also want to tie in this thought though. An object, Kendall for instance, has a specific point of her body at which, for all practical purposes, her mass is concentrated. We call it the center of gravity or the center of mass. That's really all we care about with Kendall. You see, if Kendall has any size at all, it could mess with the math. Where on her body was a force applied to her, right? For instance, if Audrey pushes on her shoulders, but her little brother pushes on her legs or something like that, okay? Well, that could mess with the math because there's what we call torque, which we'll get to in a later chapter. For now, we're ignoring Kendall's size, and Kendall might as well just be a dot of infinite smallness. We're going to assume, for the sake of math, that every force that acts on an object acts directly at the center of the object's mass. That way we don't have to worry about torques and things like that, which we will get to in a later chapter, but for now we're ignoring that. So as we work our force problems, it's going to be very important that we draw really good pictures. As you look through the chapter, you're going to see lots of pictures. However, sorry Audrey, are not artists. Our pictures are going to be very basic. We call them free body diagrams. There's the first of very few terms before you get in your notes. A free body diagram is a sketch that shows all forces acting on a body. A sketch that shows all forces acting on a body. A sketch that shows all forces acting on a body. Now, we call it a free body diagram because the body, or the object, is free of its body. All we concern ourselves with is the center of the object's mass. So in a free body diagram, the object, whatever it is, will be represented one of two ways. Typically, in a free body diagram, the object is simply a dot. No shape, no size, just a dot representing the center of mass. Now, we won't make comments as to the improved appearance of certain people in the classroom if we were to represent them as dots. We won't go there because that would be mean for us to do things like that, wouldn't it? Yeah, so we're not doing that. There are times, though, that for the sake of the drawing, we'll want a little more room to show things. So in some cases, we could show the object as a box. Every object that we draw in this class moving forward will be either a dot or a box because we're just not good artists. Okay, I'm not a good artist. Mathematicians and scientists typically are not good artists. Present company excluded. The ladies in our class actually are quite talented artists. Then we have to draw all of the forces. Well, since force is a vector and we draw vectors as arrows, it makes sense then that all of our forces will be arrows. All of our forces will be drawn as arrows. The key is every single force that acts on an object must be present. So for instance, let's suppose we have Kendall. Kendall's standing there and Audrey comes up behind her. Okay, so there's a cliff here, but we don't draw the cliff because we're lazy. And Audrey comes up behind her and pulls her back to safety. Is that the only force acting on Kendall? No. What else is acting on Kendall? Gravity. Her own weight is pulling downward. But that's not the only two forces acting on Kendall. Gravity also is acting on that pen. Well, there's another force that would be acting on Kendall. The normal force, pushing upward. Otherwise, she'd be sinking slowly into quicksand, right? There's a normal force acting on her as well. Three forces in play. Audrey pulling on her, her weight pulling her down, the normal force holding her up. Any other forces? Well, within the nucleus of the atoms of a body, there is a strong force acting on the object as a whole. No, okay? That's it, right? Those are the three forces. The free body diagram has to include everything in the picture. So, some different forces. Let's go and list some of these things out. One force that will always be present is the force of weight. The force of weight will always be present. Because our free body our problems are taking place here on planet Earth, not in outer space. That's a little unrealistic. Okay, so weight is always in play. Almost always in our problem, the object would be then sitting on something, resting upon something, standing at the edge of the cliff, sitting in a chair, resting on the floor, whatever. So in that case, if the object is resting on a surface, the surface must support the weight with normal force. So there's almost always going to be a normal force, not in every problem. You say, how would that be possible? Well, we won't use Kendall because we would never do this to Kendall, but let's suppose somebody very bad was being strung up. All right? Well, in that case, the object isn't resting on the ground anymore. The box was or chair was kicked out from under them, right? I'm not advocating any of this, by the way. All right? We're only thinking about back in the olden days, you know, where bad guys, you know, who murderers got a tall tree and a short rope, okay? But, okay, maybe less violent. An object hanging from the cable of a crane, right? Just hanging there, swinging there. It's not resting on anything. So in some cases, we may have what's called a tension force. A tension force. That'll be a force that's transmitted through a cable. Go ahead and get that definition down. Tension is force that's transmitted through a rope, cable, string, chain, some kind of connector. Maybe, again, much less violent. A person sitting in a swing out at after-school care. Little kiddo just sitting there. Well, it's not normal force that's holding them up because they're not on the ground. They're in a swing. It's the chains holding them up, right? Now, obviously, the chains are connected to the bar, which is connected to the legs, which is connected to the ground, which is held by normal force. So, I mean, normal force is still there, but for the child, for that object, if you will, it's tension force supporting there. In almost every problem, there will be some external force that's applied. Besides inherent forces, some applied force. This is usually what's triggering the action, triggering the motion. We'll notate that F sub A, some applied force. And there's one more force, coming back to Kendall. So Kendall's standing here, that's Kendall. Lovely. All right, and there's obviously weight pulling her down, there's normal force pushing up, and Audrey comes and grabs her. Now, Kendall is kind of small. It is possible that Audrey picks her up and moves her, in which case the normal force isn't so much at play. But what if she grabs her and drags her back from the edge of the cliff, desperate to save her life because she's that kind of a friend? Well, if she drags her across her feet, across the ground, then there's also friction force. And if Audrey's pulling this way, friction's going that way, isn't it? So there is another force at play here. F sub F, friction force, is often going to be a player in these things. Now, I want to consider this for just a moment. If I were to say that Audrey, this is the Audrey force, or the applied force, and here's the friction force. What if I wanted to show that the friction force was acting this way, and Audrey was pulling that way? You see, there's really no differences there. They're still going in the same direction, right? Now, in real life, if the cliff edge is here, Audrey could not possibly be on this side and push her back that way, could she? All she could do is pull. But you realize if there were a way, for instance, you weren't quite so close to the edge of the cliff, and Audrey got between her and the edge and pushed her this way, pushing her with the same force is the same as pulling her with the same force, as far as the forces are concerned. Now again, realistically, you push her, she falls down. You pull her, you're holding her up while you're doing it, right? But practically speaking, it doesn't matter from which side of the object the force is applied. One could also argue, well, the normal force is from the ground, it's pushing up this way, and weight is pulling down on the object. It doesn't matter which side of the object, as long as the arrows, the vectors, are going in the correct direction. Does that make sense? We call this the principle of transmissibility. The principle of transmissibility. Just make sure the arrow's aimed the right way. Doesn't matter which side of the object you put it on. A push and a pull are equivalent as far as the force is concerned. Again, there are other implications, but we're strictly looking at the forces being applied, not external factors. So the question is going to be, as it has been multiple times throughout this, anytime we deal with multiple vectors, well, we have all these different forces, we have all these different vectors acting at the same time, all these concurrent vectors. What's the outcome? What is the resultant? The resultant force, or F sub r, is the outcome of all the other forces. That's a term that is already fairly familiar to us. We had it with vectors in general, now with forces, since force is a vector. But think about it this way. Let's suppose Kendall is going down a slide. This is Kendall. That's the slide. All right? As Kendall is going down the slide, it's a very long slide, so we can talk about it while she's sliding. What are the forces acting on Kendall? Gravity. Now watch. Gravity pulls straight down, doesn't it? It does not pull her down the slide like this. It pulls her straight down, doesn't it? What other forces are at play? Friction. There's going to be friction. Now, if she's going down the slide, which direction is friction acting? Up. And it is acting up along the surface. Do you see that? What other forces are at play? There's a normal force. Now, remember, normal force is perpendicular to the surface. Normal force is not straight up. Normal force is perpendicular up. So normal force would be like that. Any other forces at play? Well, weight is gravity. Weight and gravity would be the same. No. Now, here's the thing. The outcome of these is she's going to end up going down the slide. There will not be, probably, enough friction to keep her from going down the slide. If it is, it's a very bad slide that needs to be cleaned, okay? But probably she gets down the slide just fine. Maybe if she puts her feet down, like you've done that before, you can stop yourself from going down the slide. But assuming she's just going down on whatever she's wearing, right? Cloth of some kind, she slides down just fine. Well, what if, though, Audrey realizes that at the end of the slide is a little kid was just on the slide, and the kid had just eaten before going down the slide, and the kid got very scared going down the slide, and there's a mess at the end of the slide, and Audrey's like, stop! Okay, there is currently a resultant force. Let's just say the resultant force is 30 newtons going down the slide like this. Let's just say that's the resultant. For Audrey to stop Kendall from going down the slide and landing in the, Audrey would have to add an additional force of 30 newtons in the opposite direction. What this would do is it would stop her progress. It would cancel out all the other forces, right? A single force that cancels out all the other forces by itself is called an equilibrant. Equilibrant force. The equilibrant is a single force that cancels all the other forces. Now, how could one force cancel all the others? if it is equal to the resultant, but in the opposite direction. If it is equal in magnitude, but opposite in direction to the resultant. So she's not going to counter the weight and the normal force and the friction force and all those things separately. What's the resultant? Okay, if it's 30 newtons down the slide is the resultant force, then all we have to do is say, okay, cancel that with 30 newtons acting up the slide. And she can stop Kendall from sliding down, and Kendall's very thankful, very thankful. That's what I do in this class. I build friendships and bonds between you because you're so thankful for each other. See, that's what we do. All right. All right. Michael, there's a reason we couldn't have you on the slide. I could stop you from going down the slide, but I don't know that Kendall's not stopping you. You're just ending up in the, it's a bad day. Now maybe Kendall could say, Michael, don't go down that slide. Like, that would be a good friend. Would you do that for him if there was at the bottom and he was about to go? Would you say, Michael, don't go down that slide? Or
she would sit and laugh.
You would sit and laugh. She would laugh. Okay. Well, anyway, glad she was on the slide, not you then. I mean, have no help. All right.
Down the slide.
Now, if all the forces acting on an object cancel, then we have something called translational equilibrium. Translational, and I can't cursive R's. Equilibrium. Okay, translational equilibrium is a situation in which there is no acceleration in the x and no acceleration in the y. Now, how do you have zero acceleration? Remember, if F equals ma, for acceleration to be zero, the force must be zero, or the resultant force, or the sum of the forces in the x, and the sum of the forces in the y must be zero. Basically, everything cancels out. Now, word of caution. There is this idea that, if all the forces cancel, then the object is not moving. Well, let's suppose Michael is walking down the hallway. We'll go with Michael this time. Michael's walking down the hallway, and somebody comes up and shoves Michael from behind. Let's suppose somebody else comes from in front and shoves Michael with exactly the same amount of force. You realize those two forces would cancel each other, correct? But Michael was already moving forward, wasn't he? If these two forces cancel, they don't cancel out what Michael was already doing. The result is that although Michael is not accelerated by either because they cancel, it doesn't necessarily make his motion stop. Does that make sense? So translational equilibrium doesn't mean that an object is not moving. It means that an object is not accelerating. Does that make sense? When the forces all cancel out. Now, if the object was stationary to begin with, then yes, translational equilibrium, no acceleration, means it will stay stationary. If the object was already in motion, then simply canceling out forces wouldn't do anything. In Kendall's case, though, it was the 30 newtons that was causing her to move, correct? So if that Audrey is able to apply 30 newtons, that would cause a cessation of motion, if you will, or cause continued acceleration. Maybe take a little bit extra force to slow the progress and stop the previous progress. But translational equilibrium means it's not going to accelerate at all. The forces will all cancel. Most of our problems will involve some degree of translational equilibrium. Flipping over here, page 132, a good write-up on Sir Isaac Newton. I've mentioned this before, but all of these write-ups, and you'll read this in your homework tonight, just points out that the great scientists, and we watched a video in chapel not long ago pointing out all the great scientists who made all the great discoveries, without fail, Christians. Why? Because who looks for order if you believe it's chaos? Those who believe in order, those who believe in a God, are looking for patterns. Anyway, page 135 now. Flip over now to page 135. And look at the example problem. I'm going to read that example problem for us, if you would, Michael.
A 35-kilogram dresser is being pushed with a horizontal force of 60 newtons. If the coefficient of kinetic friction is 0.145 between the floor and the dresser, find the dresser's acceleration.
All right, so we have a floor. We have a dresser. I'm going to go with a box this time. That's a dresser. Say it doesn't look like a dresser. I don't care. It's a dresser. And the dresser, as it sits on the floor, class, it has Gravitational force or weight that pulls straight downward. It has a certain amount of weight. Now, it doesn't sink down into or through the floor, we don't think, because the floor is able to push back up with what we call normal force. And it's just sitting there minding its own business. Then along comes a person who pushes on the dresser with a horizontal force. I don't care which direction. We'll let Michael choose since he read the problem. Do we want to push to the right or to the left?
Right.
We want to push it to the right. So we'll push the dresser this way with an applied force. But as soon as the sliding begins, as the sliding is going on, what is resisting that?
Friction.
Friction. There's our free body diagram. Pretty straightforward. We need to find all of the forces in play. Well, we're told how much the applied force is, correct? We're told the boy pushes with, or the person, excuse me, pushes with a horizontal force of 60 newtons. Now, if he pushes on it, it says at the end, you notice, find the dresser's acceleration. It stands to reason that friction will not equal 60 newtons in reply. He will exert more force than friction will exert. And if that's the case, the object will accelerate, correct? If friction were exactly 60, the formerly stationary dresser just ain't moving. Make sense? So assuming that the 60 newtons is greater than the friction force, whatever that is, we will get an acceleration. Make sense? We can find the weight of the dresser as well, because we're told the mass. The mass is 35 kilograms. How do I use the mass to find weight, class? mg, mass times gravity. So we'll take the 35 kilograms, multiply it in your calculator, times 9.8 meters per second squared. How much does the dresser weigh? $343 newtons. That's the weight of the dresser. Now, in the x component, if we want to think of it that way, we will not have translational equilibrium. At least we don't think we will, correct? We are assuming the forces will not cancel each other. But in the y, we better have translational equilibrium, or else the dresser begins slowly rising or sinking through the floor. So if there's 343 newtons down, class, what's the normal force? 343 newtons. The only reason you ever care about normal force is that you need normal force to find friction force. That's the purpose of normal force. Because we know friction can be found, class, by multiplying coefficient of friction times normal force, right? Now, we've got the 343 on the calculator. That's the normal force. What was the coefficient of friction? That is a very low coefficient of friction. And so, how much friction force is there?
49.735 newtons.
Do you see how every force has been solved for now? Notice that in the y, they cancel. In the y, we have translational equilibrium. In the x, we don't. Who wins, applied force or friction force? The applied force. Now, if my son Andrew tried to push on this dresser, Andrew couldn't push with a force of 60 newtons. Dresser doesn't move. But this person who's pushing pushes with 60 newtons. That wins. What is the resultant force, or the sum of the forces in the x going to be?
10.265.
10.265 newtons. That's the resultant force. That is the force causing acceleration. Does that make sense? Remember in the previous problems we said such and such is on a frictionless surface? Kind of unrealistic, right? We weren't ready for this next step yet. Now we are. We're going to take not the 60 newtons, but the resultant force. And to find acceleration, we can divide resultant force, actual force, if you will, divided by the mass. Well, the mass was 35.0 kilograms. So we can find the acceleration in the x by simply dividing these numbers. So take what you have on the calculator now, divide out the 35, and it's not much acceleration, but it's something. This continually is getting faster and faster. Class, we have? And rounding off to 3 sig figs, we end up with 0.293 meters per second squared. Now realistically, how often do you push something and you try to get faster and faster and faster and faster the whole time? Pretty rarely. Presumably what happens is this 60 newtons of force is applied, starts it moving, which causes an initial acceleration, and usually you level off to applying bare minimum to keep moving. Once that happens, presumably the person will level off at 49.735 newtons and just push it at a constant speed. That much force would produce a constant speed, no acceleration, once you've got it moving. But the initial movement to accelerate it from rest starts with a 60 newton force. Questions on that? All right, look at the example problem on the previous page though. The example, you actually see a picture of the dresser being pushed, right? Page 134, and you see the same free body diagram we used, except we put a box instead of a dot this time, just for fun. Well, you realize instead of pushing on the dresser, you could, I suppose, as this person did, tie a rope around the dresser and drag it. If the rope is dragged level, it is no different at all. But that's not what happens in this picture. The boy is up, or the person, I guess. I don't know if that's a boy or a man. What do we think?
It is a demon.
He looks pretty weird. He looks like if I were trying to draw a picture, that's about the best I would be able to do. It doesn't look particularly good. But anyway, the individual of unknown identity is pulling on the rope at an angle. So question, class. Is he lifting up or is he pulling back? Yes. Let's take a look at the same problem now with a different perspective. So here's our 35 kilogram dresser. It still has a weight of 343 newtons when you multiply mass times gravity, right? But now instead of being pushed, it's being pulled. But it's not being pulled horizontally, it's being pulled upward at an angle. So with a force of 60 newtons. Some of this applied force is in the x. Some of this applied force is in the y. And it's in this picture here, it was pulled at an angle. Let's just say that's a 15-degree angle. At your seats, find how much of his 60 newtons is pulling backward now. Use your calculator. And which trig ratio do we want for this x component, class? Cosine, because that's the adjacent. Take the cosine of the 15 and multiply by the 60. How much force is backward?
57.9555.
Put this in the memory of your calculator since it's a weird number. Now notice, that's nearly all 60 newtons, but there's a little bit of his force that's lifting upward. What trig function do we use for that? Sine. How much upward force is there?
15.529.
Put that in the next memory of the calculator. Now notice something. If the normal force were to still be 343 newtons, do you see the y's would not cancel? Because collectively, these would overpower this. What does that mean? Does the dresser actually start coming off the floor? Probably not. Like, just picture, you tie a rope around us, you start pulling, it's not going, for instance, if I lift upward at an angle, I could, with this desk, lift up enough to actually lift it. But you realize right now I'm lifting. Do you see my hands, they have to be lifting up a little bit, but it's still touching the floor. But what am I doing? I'm helping the ground out a little bit. The ground has to push up and support that desk, but not as much if I help it out. This guy, by pulling upward a little bit, he's helping the ground out by 15.529 newtons. That's 15.529 newtons that the normal force or the ground does not have to exert. So what would I need to do to achieve this y component equilibrium? Subtract these two numbers. How much normal force is there this time, class?
27.43.
Only 327.47 newtons now. Does that make sense? By lifting upward a little bit, he decreased the normal force. And I told you the only reason we ever care about normal force is so we can find friction force. If you decrease normal force, you're also decreasing friction force, aren't you? So if he's pulling that way, friction's acting the other way. Friction is always contrary. How do I find friction force, class? Coefficient times normal force. Now we've got the normal force on our calculator still and or in memory 3. Multiply that by the same 0.145. Let's assume it's the same floor as before. Remember last time there were 49.7 whatever newtons of friction. Now how much friction is there?
47.8.
Now there's only 47.48 blah 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 newtons of friction force. Now, he doesn't have 60 newtons still, does he? He only has 57.95 newtons in the x, countering 47.48 newtons in the x the other way. So that's changing then the sum of the forces in the x. What is the resultant force now? Ooh, careful. The 60 newtons isn't in the x. This one here is in the x. This one here is in the x. These are the two that get subtracted. Not 60 minus 47.48, but 57.95 minus 47.48. What's the resultant force in the x? 10.47 blah, blah, blah newtons. Now, to find the acceleration in the x, remember, we're still going to divide that resultant force by the mass. The mass is still 35 kilograms. So take what's on your calculator, divide by 35. What is the acceleration now? Barely increased at all. Slightly increased the acceleration by lifting upward on the rope instead of just dragging it horizontally. Not much, though. Frankly, there wasn't a whole lot of friction. It's a very low coefficient. Questions on this? All right. We're going to be working on problems like those in the future, where again, we'll break everything down into x's and y's. We'll get the y's to cancel, sometimes with the x's to cancel when we have translational equilibrium. Sometimes we won't. Sometimes we'll find acceleration when we expressly do not have translational equilibrium. Homework for this evening, you're going to read over pages 130 to 139. There's a lot of example problems. Look them over. You don't have to do all of the examples, but look them over to where you kind of understand what they're doing. Read pages 130 to 139. On page 142, you're going to answer 5 questions. Numbers 1, 2, 3, 7, and 8. Page 142, answer questions 1, 2, 3, 7, and 8. And we'll pick this up in our next lesson. Have a wonderful rest of your day, and you are dismissed.